one of the most important topics in this course because we will need it a lot. You remember what we're talking about, these plans? One of the first things that you need to do about this, and I showed you some calculations from last lecture. One of the first things that you need to do is drawing your shear force diagram and bending moment diagram, simply because by doing that, you get a clear image of your beam. So that's in terms of understanding for the engineering aspects. In terms of understanding for our course aspects, guys, your shear force diagram, bending moment diagram will at least have about 20% of your final exam. As we agreed, there's no mid-semester exam. You will have only your final exam and it will be face-to-face. This is the point I'm trying to make here, and I'm hoping that everyone is clear on it. In the final exam will be face-to-face. So wherever we can get away with, guys, now, please do not trap yourself for the end of the semester, because your final exam will be face-to-face. Wherever you learn is the only one thing will help you that exam. If we got away with some help from our colleagues today, and I do understand that, please don't rely on this a lot. The shear force diagrams, bending moment diagrams will have about 20% of your final exam, plus we have a quiz of this. So we're clear that next week we'll have a quiz for bending moment diagrams and shear force diagrams. That will be about the same thing, 2.5%. So that's about 22.5, about a quarter of your grades just on one topic. Okay, so very important topic. Therefore, today we almost repeating every single thing we went through last week, but for the bending moment diagram. So please, if you're not clear on it, we don't want to get to a situation like the trusses. From now, tell me I'm not clear on this, not clear on that, and I'm more than happy to go over it once, twice, 3 times, as much as it takes to get it done. So in terms of what we learned so far, one way to do the shear force diagrams and bending moment diagrams is to take sections at every single point almost, or the critical points of a beam. Just to go back, we are learning how to analyze a beam. We looked at trusses in the first 2 lectures. Now we are starting with beams. After we finish with beams, we're going to start with columns. So in beams, the efficient way for calculating the maximum moment and the maximum shear in a beam, which is very important for design, is to draw the bending moment diagram and shear force diagram. To do that, we establish few rules. If you remember, if we have a point load applied on the beam, the first thing we need to start thinking about is the shear force diagram, how to draw the shear force diagram. Because the shear force diagram, let's look at that. The shear force diagram will be able to obtain it from the free body diagram. The minute we can draw the free body diagram, using this method, we can obtain the shear force diagram. And after we do that, we can start drawing the bending moment diagram. Using the same exact rules. The first rule we learned, if we have a point load applied to the beam, that point load for the shear force diagram will create a jump or a dip. In other words, that will make the shear force diagram go up, like here, what we have on the reaction, or down. That's a dip and that's a jump. Okay, so going vertically down or vertically up. Obviously, the direction of that movement will be equivalent, the direction will be the same as the sign of that force. If we have the force pointing downward, that means the movement or the change will be downward. If we have the sign is positive, which is the force pointing upward, that means that that movement will be upward here. That movement will be a jump and moving upward. Are we clear on the effect of a point load on a beam, guys? And please, I'm more than happy to know that someone forgot everything about last lecture, because this is the first time you're coming across this new concept. So please don't feel shy to say so. if you'd like me to go in details on this.
Aaron, I'm okay, but I think with that, I think you're gonna explain later. I'm just not that clear when we talk about a non-uniform loaded,
Yep.
like a triangle. But I
Yep.
think you're gonna explain later. Yes.
Yes, definitely. Okay, so that would be
Okay.
our third case. This
All
is
right.
starting from the simplest all the way as we go further for the more complex cases. The first one, the simplest one, is the point load, and that's straightforward. Okay, so we took an example of that, and we said in this example, obviously the first thing we need to think about is the free body diagram. Now I have two forces here. These two forces acting upward, that means they are positive. I've got one negative force. So from this, we agreed that any forces acting downward are negative, any forces acting upward are positive. Okay. Based on this concept, based on what we learned, my shear force diagram should go up by 10. Then in between these two forces, there's nothing. Look at it in the beam, there's nothing there. That will stay, that will maintain its last value at 10, and then will dip down by 20, and then will maintain that value, and then will go up again by 10. We have to make sure that we start at 0 and we finish at 0. That is a good way to make sure that our shear force diagram is correct. So that's what we've done for those cases. We went up straight down by 20 from positive 10 to negative 10, and then maintained the same value and then went back to 0. Here, please, all of you, when you draw this type of diagrams, the shear force diagram, please nominate which one is positive, which one is negative. Just put here some positive and negative, please. It's a good thing for you. You will need it for bending moment diagram, because the same concept we have, which is we need to know, is it positive or negative to decide on our direction for the next one. Okay. So that's the point load. We took an example of that. Now for the UDL, uniformly distributed load, just we learned that for a uniformly distributed load, everything would be exactly the same. The only one difference, that the shape of the shear force diagram, because of a uniform distributed load, will be different. So if I have a uniform distributed load like this, that's the free body diagram. That's always, we have to calculate our reactions. So step one, we need to always calculate our reactions. This is our free body diagram. Now, as you can see, the shear force diagram under the influence of uniform distributed load will be different than point load. We'll start making a diagonal. That means not straight. That's what I'm referring to as diagonal. It could be increasing or decreasing. It depends on the direction of the force. And we just said it a minute ago. Any forces acting downward, all these forces, you can see them acting downward, they are negative. That's why my sign here, or the direction, is going downwards. So the shape, a straight line, look at it, the uniform distributed load is a straight line. Straight line will make diagonal line. The sign is negative here. I'll add that. So, on it. This is negative. The sign is negative here for the force. That means my direction is going downward. Okay? How much does it go downward? Is the area underneath this rectangle, which is 10 by 4, the distance. 10 by 4 is 40. We started, why is it 5, 10 kilonewton. So the reaction here is incorrect. Sorry, that should be 40, that's 20. And that will be 20, negative 20. Okay. So We did this question anyway last week. I did this quickly before I sent you the slideshows. So we go up by 20, then how much the lowest value we are getting to is the area underneath this rectangle. 10 by 4 is 40. We were at 20 positive, going down by 40. That will give us 20 negative. So this has nothing, please don't use the reaction. Do you remember what we discussed, guys? Do not use the reaction here to tell you how much you need to go down. You use the area underneath the rectangle. Are we clear on this? Does it make sense what I'm saying? So do not use the force here to guess how much you need to go down. This will not be always the case, especially if you have any forces outside here. So how much the line would go down is the area underneath the rectangle. In this case here, we took an example. The reaction up, and then under this area here, this portion of the beam, the shear force diagram will be diagonal line. That diagonal line will go down by the value underneath this rectangle, which is 4 by 1040. We started at 17.75, negative 40, that will make negative 22.25. And then we go up by the reaction, and then we stay straight, okay? Now for the UVL, uniformly varying loads, the last case, it's exactly the same as UDL, guys. The only one difference is the shape. And that shape will have a new rule for it, which is the shape will be curved to start with. So here we said a straight line will produce diagonal line. What about if I had diagonal line, which is a UVL? Can't make another diagonal line. Has to go one step further, has to go 1 degree higher. The 1 degree higher than a line with a slope is a second degree curve. Okay? Second degree equation, or a curve, parabola curve. So the shape, we know it's curve. Now, because it's a curve, you have too many cases for a curve. This curve could be increasing or decreasing, like that, decreasing. And that curve, even if it's increasing, we have two cases here. This curve could be increasing facing down, like what we got there. This is hogging. I'll put an H here, facing down, hogging. Or could be the same curve going up, but facing up. Look at the curve, facing up, that's sagging. Or even it's going down, you have the two cases, either facing up, which is sagging, or facing down, which is hogging. Okay? This is just possibilities. You don't have, this is too much to think. That's why we're not going to do this and think about all of these cases. This is ridiculous. What we need to do, we have to apply our rules. Our rules tells us if you have a diagonal line, that will produce a curve. And let's say the forces is like this, uniformly varying loads. Okay? Negative, when we say negative, I'll just say 5 kilonewton per meter and 0. This 5, is it positive or negative, guys? That's the first thing you need to know.
It's negative.
We just agreed that all the forces acting down are negative. Always keep that in mind, please. Okay? So we know it's negative. The second thing, just keep that in mind. So that means the first question I'm asking myself, the shape. Always write them down for yourself like this: sine and sag or hogging, if you would like, or the curve direction. We'll talk about this in a second. What's the shape here? We've got a diagonal line already. What would that produce? We agreed that will produce a curve. So shape, that will make a curve. Okay. Now the sign, is this positive or negative? We said it's negative. That will produce a declined shape, curve. So we've got curve, declined. Now curve, declined, that means this is our possibilities. Look at them. These two are curves and both of them are declined. That means going down. The one thing we need to know, is this a sag or hugging curve? In other words, is it facing up like this or is it facing down like the hugging curve? And the answer to this, it's depending on your value here. Is it increasing or decreasing? So my first value started at 0. I went to -5. Don't forget, this is a negative. 0 to -5. Is that increasing or decreasing?
Decreasing.
That will give us, that's this right here, decreasing. And that will give us hugging curve, which is this one here. Decreasing, that means facing down. So I know now the bending moment diagram for this, if this is the force like that, the shear force diagram for that, this is the beam. The shear force is a curve, declined, and facing down. Easy. Done. How much? This value here, the maximum shear, is the area underneath. Always, the maximum value of any curve is the area underneath the other curve, or the previous curve. How much the area underneath this curve? I've got 5, let's say it's 4 meters. 5 by 4 divided by 2, that's 10. -10 kilonewton. All right, guys. So if you just keep an eye on these 3 questions, you'll be instantly securing 25% of your grade for this subject. Won't take you long at all to draw this. Yes, Freddie.
Yeah. Just can you show us again the last part, those -10 kilonewtons there in your left hand side?
This one here.
Yeah, please. Yep.
Okay. So all I'm saying, the maximum value for any curve is the area underneath the previous curve. So the maximum value in shear force diagram, it's the area under the free body diagram. Okay. What's the area underneath? If I've got this one 5 and let's say the distance here is 4, how much the area? Can you calculate the area of this triangle for me? 4 by 5 divided by 2, correct?
Yep.
Which
That's
is
-10.
10.
Yeah.
Okay.
That is
Why minus? Because it's negative. We agreed it's going decline below 0.
Yep.
All right, guys. So I'm not relying on this too much because that's exactly what we'll be doing today. So it's your chance, even if you don't, because I do understand it's a new topic, guys. That's the first time you look at it last week. If you didn't gather almost anything from last week, today is your chance, please, to practice it, work on it, and ask questions and be good at it. Because next week we have a quiz.
Sorry, Aaron.
Yes, ma'am.
I'm reading on the table.
Yes.
So
Which table?
I think
This one here?
Yes. I think there's a little bit of confusion created by when it says that if UVL magnitude is increasing, the curve will be facing up, or if it's decreasing, the curve will facing down. If you could go please to the diagram you drew before.
And explain that.
I just want to say something to.
Yeah.
So the thing is that if we look at the UVL now,
Yes, here.
It makes me think that the magnitude is increasing.
Yes, yeah. So the word magnitude I'm saying here as a value, the actual value is in terms of positive or negative. The magnitude is increasing, but in the negative direction. What does that mean? So I'm starting. Okay, you're looking at the magnitude here is increasing, correct?
Yes.
But in what direction is it increasing? In the positive or negative?
it's increasing in the negative direction.
That's what I'm referring to, as if that means overall it's decreasing. So if that will make you I was very hesitant to add that word magnitude. If that will make you comfortable, you can just simply do that. Where is it? Don't worry about the word magnitude. Okay, because any vector is made of a magnitude and direction. Remember what we learned at the start? You can say if the UVL is decreasing or increasing. Okay? Or the value, if you would like to say. Make sense? No, not yet. Okay.
Could we have an example of the other one, of the sag curve? Maybe that will clear up things.
Of course.
Thanks.
Let's look at it here next to it. Exactly. Which is, let's have the same thing here. 5 kilonewton. Well, like this. Okay? If I have that, and I'm saying here, let's assume this is the same thing, a cantilever beam. Okay? And I've got the forces acting downward. So the shear force diagram for that, if we follow the same thing, it's curved. The sign here is negative, so it's decreasing, the same thing, correct? But the magnitude started at -5 and finished at 0. Look at it. I don't want to show the support here. Started at -5 because that's negative. All of these values are negative. -5 and finished at 0. What does that mean? That means the curve is increasing. The value is increasing from -5 to 0, increasing, rather than from 0 to -5. That means my curve should be in theory facing up. So the same thing, it's a curve, declined curve, and the same value underneath, -10, but the shape of that curve is facing up. Make sense? If that's 4 meters.
Yes, thanks. That's clear.
If you would like, which is, I never tried this before, but maybe that will make it easier for you. You can imagine all uniform distributed load, draw them on the under. If that will make it easier for you, whenever we have UDL or UVL, draw them if you would like on the underside of the beam. So this one will be like that. And the force is acting downward. That one. From -5 to 0. You can do that. Or this one, for example, you can draw it like this. 0 to -5. If that will make it any easier for you, that will make it easier for you to visualize it. So you're saying here, my value of the force is decreasing, my value of the force is increasing. Draw these forces if you'd like on the underside of the beam, which is, with time, you will be able to visualize it straight away looking at it normally. Anna?
So my question is, if when the force is increasing, as the second one on the top, so my curve have to facing up or down?
Up.
Okay, so when it's increasing, the curve have to facing up.
That's correct. So if the force is increasing, the curve will face up. Look at it here.
Yes.
If the force is decreasing, the curve will face down like that one.
All right. Okay, I got it.
Okay?
Thank you.
So
Yes.
the good thing about this method, guys, it's everything in line. Anything positive up, anything negative down. increasing up, decreasing down. Okay, you don't need to memorize it. It's just everything positive up, everything negative down, either in direction, where the curve is facing, all of those aspects. Anna, did that answer your question? Okay, if you still,
Yes.
okay, good. If you don't mind, then if you can lower your hand. And we've got, who else there? Someone else did have a question? Okay, so let's summarize all of this at the end here. We took some examples. These are the two examples that we looked at. This is our summary. So I'm not including in this summary, I'm not including point loads, because point loads, it's something easy. I'm not going to worry about it. We are all agreeing with this, guys. Point loads are straightforward. Wherever the point is acting, the shear force diagram will move that way. But now the next level after that, and all of those cases a bit more complicated. Regardless, is it free body diagram or shear force diagram? Doesn't matter if we are trying to draw a shear force diagram or bending moment diagram from the free body diagram or the shear force diagram, we have the same set of rules. The first question I want you to ask yourself is the shape parameter. What's the shape of my shear force diagram or bending moment diagram? And the shape, these are the three cases you have, which is very straightforward. Flat line will produce a diagonal line. A diagonal line will produce a second degree curve. A second degree curve will produce a third degree curve. Okay? Are we clear on the shape? So a normal flat line, which is uniformly distributed load, is a flat line. That thing there. That is considered a flat line. Look at it. The top of this load is a flat line, continuous. That will produce a diagonal line. A declined or inclined or diagonal line like this will produce a first degree curve. Sorry, second degree equation of a curve, which is a parabola curve, if you'd like me to be more accurate. If for any chance, and that will happen more in the bending moment diagram, you have a second degree curve, the next one level up is third degree curve. How different in shape? That's the question you may ask. What's the difference in shape between the two? It doesn't concern you. And by eye, you won't be able to notice the difference because we are taking just a small portion of that curve. We're not seeing the overall shape of the curve. There are two different completely curves if you see the overall equation, but we're talking a small portion of it. So you won't be able to tell the difference. The important thing for me that you just write next to it, second degree or third degree curve. That's all. And you know, where does it curve, up or down? Which is we'll talk about in a second. So just to go back before I ask you, Freddie, to ask you a question, our first rule only is the shape. The flat line or the horizontal line will produce a diagonal line. The diagonal line will produce a second degree curve. Second degree curve will produce third degree curve. Freddie, did you have a question?
Yeah, Aaron, it's about the third degree curve. I got the second degree curve. I understand that point, but I don't know how you get the third degree curve there.
So what I was showing you an example here, and that's what we're trying to understand. When I'm showing you this example, this is a second degree curve. We agree because that's the diagonal line will produce second degree curve, correct?
Yep. Yep.
And that's my shear force diagram. If I write here, I'll write shear force diagram. If I need to draw the bending moment diagram for this, I'll do exactly the same steps, which is the first thing I need to ask is the shape. This is a second degree curve. That means my shape here will be third degree curve. Third degree curve, as I said to you, won't make any difference other than it's not the same curve. That's all what you need to know. We will follow exactly the same rules. Is the sign here positive or negative, Freddie?
What do you mean positive or negative? The 5 kilonewtons going to 0, that is positive. Is
no, I'm talking about the shear force diagram. This area here, is it positive or negative?
I will say that is positive.
It's negative. Why would you say it's positive? Look at it. It's all under. We draw this under the beam on the negative side, right? And the value we got here is negative. Maximum value is negative. Do you remember what we said? This is a decline. So that means going from 0 down. So the overall sign here is negative. That means, again, this will give me a declined curve. Now I know two things. I know the shape is a 30-degree curve. I know it's a decline going down, not up, going in the negative direction, not in the positive direction. And the third thing we need to know, where does it face, up or down?
Up, facing up.
This is our value here. We started at 0 and we ended at negative 10.
Well, it's going down, but the curve is. Are you talking about the curve, where the curve is facing?
I'm talking about the new curve that I will be drawing. I'm trying. Okay, for any curve we need to draw, we said we need to ask ourselves these questions: the shape. The first thing we need to ask, the shape. The shape. We've got the direction, or the sign will give us the direction. And is it sag or hugging, or is it facing up or down curve?
Okay.
So I'm starting with the shape here. The shape, it's a 2nd-degree curve. So my judgment, in my mind, what I'm saying to myself, 2nd-degree curve will produce the 3rd-degree curve. In my mind, I'm saying my sign here, this area all in negative. That means I've got negative sign. That means my curve is declined. So it's going down.
Yep. Okay, cool. Yeah. Okay.
The third thing I'm asking, is my value here increasing or decreasing? If I start at 0 and I finish at negative 10.
So decreasing.
Decreasing. So my value is decreasing. That means my new curve is facing down. Or in other words, I can say it's hogging. The engineering name for that is hogging curve.
Okay.
So I got my specification.
Okay.
My specification says that it's a curve, declined and facing down. That's
okay. Cool. So the basically, so the third curve comes from the second curve.
Exactly. The same exact thing, and that's my bending moments.
I was mixing everything, the first one with the third one. So okay.
Yep, that's good. So always we jump from one stage to another.
Okay. Yeah, that is was my. I was mixing everything. So yeah, I got it now.
Okay, good. So how much the maximum value here, the bending moment diagram will reach? It's the area underneath this curve. Anyone will remember what's the area underneath this curve?
It's I know you're asking about the area.
Yes.
It's the definite integral of the function.
Okay, that's a good way of doing it, but there's an easier way of doing that. Paolo would know.
W power of 3.
Sorry? Who's that? Fabio? Is that Fabio trying to say something?
Yes.
Why is it?
W to the power of 3.
W to the power of 3, yeah, okay.
Times L divided by 2, if I'm not wrong.
Times L divided by 2.
right
So
or not?
the area, guys, the area. Paolo, do you have something to say?
Sorry?
Do you have something to say about this?
About the area?
About the area, about the maximum value here.
So will be, I don't really remember.
Okay.
I know it's I think to be WL to the
Okay,
third.
no, that's not what.
6.
If you don't mind, that's not what I want. I want you
Okay.
to understand it. Let me just show you something, guys. And that's so you can remember it for good now. If I have a triangle like this, and let's draw that again and again.
That base times height divided by 3?
Yep.
Okay.
Okay. So, guys, if I have a triangle like this triangle, the area of this triangle, A, equals to, obviously, 0.5, half of, let's call this one height, and let's call this one the base. Half the base multiplied by the height. Why? Because simply, think about it, this is half of this rectangle. The rectangle area is base by height. Half of it is this triangle, which is half base of the height. This is obvious for everyone. Now, if I have a second degree curve like this, the rule about this, rather than half, rather than 0.5, would be thirds. So rather than, let's just rewrite that in a different way. The area here, this is A, and always this is B and H. The area here equals to A equals third B by H. If that's, so in other words, I'm saying the area of this is third of this, again, of this rectangular area. That means what's the area here, guys? If this is third, that's 2/3. Let's call this one A2, if you would like. This is A1. A2 equals to 2/3 of B by H. All right? They both make the same triangle, rectangle. So the same thing, if I would say, if I have a second degree curve like this, and I'm asking for the area here, that is obviously A equals to the 2/3 of B by H. So it depends which one I'm asking you for, the smaller or the larger one made by this curve, by a second degree curve. If the smaller is the third, if the larger is the 2/3. This is our case here, look at it. It's second degree curve and I'm asking for the larger area because if I continue this to a rectangle, this will be the smaller here and that will be the larger. So the area of this is 2/3 multiplied by the base by the height. The base is 4 meters, the height is 40, multiplied by 2, that's 80 divided by 3. And that will be your maximum value here. So there'll be 80 on 3, I think would be. Okay? So you can get straight away the answer for that. Are we clear on this? That's the only, you will not get to a point you need to calculate that. you will not get to a point you need to calculate the area under a 3rd-degree curve. The maximum area we need to calculate in here is under a 2nd-degree curve. So, are we clear on this concept here, guys? Anyone would like me to explain it again? Okay, good. Just keep in mind, please remember it as if the triangle is half of the rectangle, this area under the 1st-degree curve is 1/3 of the rectangle. 1/3 of it. 1/3 B by H. Okay. Now, if I go back to our PowerPoint slides. So far, what we agreed on, the first question, and you have to ask yourself, guys, in the right order. What's the shape? What's the sign? If you have a curve, this is only if you have a curve, reduced curve, you will ask yourself this question. If you don't have a curve, you don't have to go there. But we start first, what is the shape? That's the rule about the shape. The sign will tell us the direction. Is it increasing or decreasing? Is it going up or going down? This is the sign here, giving us a result of it. We're getting the direction. Are we going up or down with our shape, what we produced from here? And then the last thing, if our shape was a curve, we need to understand. We need to decide: is our curve facing up or down? Facing up, we call it sagging curve. Sagging is a smiley face, and curving down, facing down, hogging curve. So you remember this when you learn geotech engineering, footing design. The shape of the slab doing this, we call it hogging slab. The shape of the slab doing that, we call it sagging. The same thing for a beam, the same thing for a road, for a curve. We'll talk about those, okay? So, this is all your lecture, this table here. As long as we do understand this table and we know how to apply it, we should be fine for the most complex shear force diagram and bending moment diagram. Any questions about this table, guys, before we start doing some examples? Guys, all good? Okay.
Yeah, all good, thank you.
Perfect. All right, let's do an example then. This is our example here. Simple one, doesn't have any shear, doesn't have any UDL or UBL. Just simply, we will do all cases today. Don't worry about this point here, guys. We are going to draw shear force diagrams and bending moment diagrams, so it won't be just shear force diagram. So for the first one, would you be able just to help me with it? Okay. So the first thing we need to draw is the free body diagram, and we need to calculate reactions. So to calculate reactions straight away, I'll take sigma m, and just choose a lighter. That's it. So I'll take a moment around B, for example, sigma mb equals to 0. That means I've got the 50 kilonewton acting at 3, and that's rotating clockwise. And I've got the 30 kilonewton acting at 1 counterclockwise. And I've got the reaction at D. I'm assuming the reaction obviously always vertically facing up. The reaction at D acting at 5 meters and turning around B counterclockwise. So that is negative R dy multiplied by 5 equals to 0. So if I move all of this to the other side, okay. For the next ones, I'm not going to do it personally, but just we'll do it now. I'll take all of this here. In fact, I can do that. I'll take, look at it, guys. I'll take all of this and I'll move it to the other side. If I move it here to the other side, I have to change the sign. That means this is gone. And the 0 obviously is gone. I know some of you guys very confident with those basic maths, but we are all going at the same speed, making sure that everyone on board. So that means dr dy equals to all of this divided by 5. That's 10 by 3 if I cancel. That's what I'm telling you what I'm doing in my mind. So I've got this one divided by 5 will be 10, and this divided by 5 will be 6. So I've got 10 multiplied by 3, which is 30. Take 6, that will give me 24. So r dy equals 24 kilonewton. And otherwise, if you'd like, if you prefer, you can use your calculator. Okay, whatever is easier for you. So that's 24 kilonewtons. Now, if I need to find the reactions here, that will be 50 plus 38, take 24, that is 56, I think would be. So what I did here, sigma Fy equals to 0. Sigma Fy, let me just get rid of that since we finished all of those. Sigma Fy equals to 50 downward and 30 downward, that's 80 negative. And I've got 24 positive. Plus I've got 56. Sorry, I don't know that yet, which is Rby equals to 0. If I move all of those to the other side, it will be Rby equals to 80. That's changing the sign on the other side, negative 24, and that will be 56 kilonewtons. Okay. So we got our reactions. That's a simple step that we have to do every time. Now we start with the shear force diagram. As we agreed, please try to, when you draw a beam, it's way easier for you to use the ruler on your paper. It's not the easiest for me to use. But when you draw the shear force diagram, bending moment diagram, try to keep it organized. Just draw these like this to start with. Make it easier for you. And try to just trace those down roughly, so you understand where you're going with this, okay? Okay, the shear force diagram. What do we have here? A point load at 30 Newton acting downward. What would that produce, guys? I can't see can you please just open your microphone if you've got something to say?
Going under the line there.
Yes, the beam. And so going, let's put it that way, we are going in the negative direction. How far do I go and what shape? Is it straight down or an angle?
It's straight down under the beam by 50, I reckon.
50?
30.
Okay, 30. Perfect. Did you say 30 at the start or did I hear you wrong?
No, I say 50 first.
Okay.
Yeah.
All what we have is 30. Okay, that's where we're going down. So negative 30.
Yeah, 30. Sorry. Yeah, my mistake. Yeah, by 30. I was checking the middle one. Yeah.
That's okay. All good. So we are going down negative 30. And between these 2 points, there's nothing acting. That means I've got nothing happening there. That will stay straight. All the time here is negative 30. Nothing changed. And then what will happen there, Anna? I'm going to ask you guys to help me with those. Anna, what will happen at this point, do you reckon?
So it goes up 50. Is it 56 or 50?
That's a 56, sorry.
So it's 56. So it goes to 36.
So 56 take 30 will be 26.
Sorry, 20.
That's all.
Yeah.
All good. That's all good. Okay. So that's correct. So that means we are going up by 56 altogether, roughly the same distance there, and that will be 26 positive. And this point onwards, GM, what do you reckon will happen, Gianna?
Can you hear me?
Sorry?
Can you hear me?
Yes, I can.
Yeah. So go straight to the right.
Yep.
To C, point C.
Trying to go straight, yep. And then what will happen at point C?
Going down by 50.
Going down by 50. So I've got 26, take 50, that will be?
Minus 24.
Negative 24. And Hannah, what will happen here, mate?
Going straight to point D.
And then?
And then up.
Up by? Perfect.
To get 0.
Perfect. And that will give us 0 here. That's negative 24 again, and goes to 0. Okay, so here, guys, just please keep an eye on the steps I'm doing here. Here, I'll write here negative, so I can remember that, positive and negative. Now, Mr. Paolo, what will happen here for the bending moment? So this is my free body diagram. This is my shear force diagram. Now let's start with bending moment diagram. So you see, it's nothing different than what we've done. Doesn't matter what the names is, all what it is, we are extracting one diagram from the other. If I'm extracting this diagram from here, which is in other words, mathematically speaking, I'm integrating. If I will integrate this here, what would that give me? So let's look at what do we have here? Do you remember? We have 3 questions: shape, sign, and if I have a curve, this sagging or hugging, S and H. So the first thing, what's the shape I've got, Paolo?
Yeah.
What's the shape we're starting with?
Diagonal line.
Say it again, sorry.
So a diagonal line.
Okay, so that's the produced shape, but we're starting with a flat shape, with a flat line or a horizontal line that will produce a diagonal line. Perfect. So let's call it DL, diagonal line. Okay, is that diagonal line going up or down?
Should be negative because the area is negative as well.
So that is going down. So that's going down. Okay, why? Why Paolo is saying this? Because he's saying the area here is negative. That means the sign is negative. That will give me a line going down. So I know now there's a line is going down. Is it sagging or hugging? For a line, this will not apply. Correct? So this here doesn't apply because I'm drawing a line. It can't be sagging or hugging for the line. So that means all what we know now, it's a line going down. How much does it go down, Paolo, do you reckon? That's the second question.
Should be 30 because it's 30 times 1 meter.
Perfect, perfect. So it will go down by the area under this shape, guys, which is 30 multiplied by 1, or negative 30 multiplied by 1. So it's going down from 0. Always we starting from 0. From 0, I'm going down, so negative 30. Okay, I'll write it on the other side. All good, guys? Anyone had a problem with this? You see, at this point here, guys, look at it. I can't just do this. I don't care. I don't need to look at the shear force, the free body diagram. All my work will be based on the shear force diagram. That's it. Think about it this way, as if you're drawing shear force diagram from a new free body diagram. So, Mr. Severio, what will happen after? I'm at negative 30 here.
So we have the area of the top side that is 78. And
The area of the top here,
the
70.
top rectangle.
Yeah. Let me just add these measurements. So this one from here to there, it's 3 meters. And that's 2 meters. And that's 1 meter. So you're saying the area here is
78.
if you'd like, you can just write them down here. 78. Yep.
So basically, it's a straight line going up because it's a positive area.
You're saying straight line going up here?
No, diagonal. Sorry,
Okay.
straight. Yeah, so it's
Okay.
diagonal line
Yes.
going up.
Yep. So simply the shape first, it's a diagonal line because I have a straight line here.
Yes.
And because of the sign, it's positive. I'm just trying to break it down for someone looking at it, new guys. The same thing, again, shape, sign, and if I have hogging or sag, which is in our case will not apply because our shape is line. But the shape is diagonal line because I have a straight line that will produce diagonal line. Either from this point here, I start from here, either I'm going down or up. Because the sign is positive in this area, that means I'm going up. How much I am going up?
Minus 30 plus 78.
Exactly. So I was at negative 30, add 78, and that will be ending at this point here. So that will be a 48 altogether, correct?
Yeah.
Okay. A bit challenging. Roughly. Okay. Now, what will happen after this, Brunei?
Yes.
What will happen from this point, you reckon?
So you subtract the area of the bottle, so it's 24 times 2, so 48. So we're gonna go to 0.
But okay, how did you decide you're going to go to 0 this way?
Yep.
Are we going to go to 0 this way?
No.
Yeah.
Inclinate to the end, like inclinate 48 to 0.
So I'm going to go that way. And again, guys, just to make sure we're not guessing. Wasn't that we are guessing, well, look at them, they match each other, 48, and I can go to the 0. Not all the time you may finish at 0. There's lots of other things that you have to take in account. Let's make sure that we are following the rules. I've got a straight line that should produce a declined line. The sign here is negative. That means this line is declined. How much is it? 24 multiplied by 2. And that's your bending moment diagram done. All good? Okay, it's 12:37. Shall we have, do you want to have your lunch break now, or at 1 o'clock shall we have it? We've got plenty of exercise to be done today. Let's do another one. Let's do another one first before we go to lunch break. Or are you writing anything? Let me check. All right. All right, let's have lunch break now, guys. You want to have your lunch break now? Or I don't mind, to me. Okay, good. All right. Lunch break will be 30 minutes, okay? Let's come back in half an hour. But that's it. We're not having any breaks today anymore. We'll continue until 4 o'clock. What will we be doing, guys, so you know what we're doing after the break, we'll be doing as many examples as we can, just mastering the shear force diagram and bending moment diagram. So please, today is your chance to prepare for next week's quiz, put it that way. All good? And you're 20% in the final exam.
Yeah,
okay.
All good. I think what will be good, like you just made one example of just point and load. Then the second would be nice, like uniform distributed. And then the third one, the non-uniform, would be nice to compare like the three cases straight away.
Are we back?
Okay, we will have all the cases. We'll take that into account. Thanks for that, Fabio. Okay. All right, I'll see you after the break.